Okay, the second lesson on circular motion, we're just going to talk a little bit about centripetal acceleration. We mentioned this in the last lesson, but it's just really to tidy it all up and introduce a couple of new formulas. The main idea is how can you be accelerating but be moving at a constant speed? Which direction is this acceleration when you're moving in a circle? And what is centripetal force? Can we define it with an equation? So centripetal acceleration. We know that from last lesson, if you're moving in a circle at a constant speed, your direction is constantly changing. So in terms of the acceleration, this must mean that you are accelerating. Why is that? Acceleration is how much the velocity changes with respect to time, and velocity involves direction, because the velocity at any point, if you look at the blue dot, it's along a tangent to a circle. So the arrow labelled V is constantly changing direction. This change in direction is always towards the centre of the circle. This is what the word centripetal actually means. So it's termed centripetal acceleration. We have a formula for it. We don't have to derive these. So we say that acceleration is v squared over r, and we can insert r omega as v. And if we square r omega to end up with r squared omega squared, the r on the bottom of the equation cancelled out. So we just end up with centripetal acceleration as r omega squared. Okay, centripetal force. Easy to get an equation for centripetal force using force equals mass times acceleration. Newton's second law, we can develop these equations by just shoving an m in there. F equals mv squared over r, and F equals mr omega squares, using the two equations that we've just gone through, really. Okay, did this check out with the tennis ball? What I mean by that is, in the lesson you could have been, or you should have been, swinging a tennis ball around on a piece of string with some Velcro, and you were working out or looking at when did the string or the Velcro break and cause the ball to fly off at a tangent. If you look at the formula for force, the centripetal force is governed by mass, velocity and radius. The bigger the mass, the bigger the centripetal force required. The bigger the velocity, the bigger the centripetal force required, and the smaller the radius, the larger the centripetal force required. Okay, what about work done? This is sometimes a little question they ask on exams. The force is at right angles to the velocity, so there is no displacement of the object in the direction of the force. If you look at the diagram with the blue dot again, the displacement never changes. The displacement is the radius of the circle, and it's constant. So in the direction of the force, there is no displacement. So if you're using a force equals work done equals force times distance, then there is no distance, there's no displacement, so the energy or the kinetic energy of the object is constant. Okay, let's do a very quick exam question. It's about a stone. If we whirl a stone around our head, it's a 0.5 kilogram stone. It's attached to an inextensible string, that means it can't stretch. It's whirled in a vertical circle of radius 0.98 metres at a constant speed of 7 metres per second. We'll take gravity as just being 10 metres per second squared. Just to simplify things, we need to calculate the angular speed of the stone, the centripetal acceleration of the stone, and the least tension in the string. So we're going to have to think about gravity to do part C. Part A, first of all. Angular speed of the stone, you're given a formula, omega equals v over r. We've got velocity of 7, we've got a radius of 0.98, easy there, 7.14 radians per second. So what about the centripetal acceleration? Well, we've got acceleration equals v squared over r up here. So again, we've got velocity, 7 squared is 49, divided by the radius of 0.98 metres equals 50 metres per second squared. Finally, the harder bit, the least tension in the string. Well, if we didn't worry about gravity, we could use F equals ma. So the force would be 0.5 times 50, which we've just worked out. We obviously could go back to mv squared over r, but we've just worked out the acceleration, so I've just used the acceleration of 50 straight in there. That gives us a force without taking into account of gravity of 25 newtons. But you've got to think that this thing is being swung round in a vertical circle, so occasionally it's going to be working against gravity, and the other part of the circle is going to be working with gravity. So sometimes it's going to be falling, sometimes it's going to be rising. The least tension is when the centripetal acceleration of 50 is in the opposite direction to gravity, which I'm taking as 10. So that's 50 minus 10 of 40 metres per second acceleration. So if we just shove that into F equals ma, we get the minimal force of 20 newtons.